Hello and welcome. So in this video, it's going to be quite a video, but this is going to end up being several videos, this one probably being the longest, and we're going to go over basic EKG interpretation. So out there's classes that will get you a certification or whatever in basic EKG interpretation. And everything that I cover in these videos will be the equivalent of that, so it'll be the same material and all that. So if you're preparing to take that class, or if you are taking it and having trouble, this might help you out a little bit. So yeah, this video is going to be pretty extensive, but it'll be the longest one, most likely. But yeah, just hang in there, because it's just going to be long probably. But this is also the hardest one. Like if you get through this video, then the rest shouldn't be that bad. And yeah, it's kind of cold down here, so I'm wearing a hood. Just so you know, and my hair is kind of messy. That's why I don't always just walk around inside with a hood on. I just thought I had to clarify that. So anyway, so let's get started. So in this video, we're going to cover intro to EKGs, monitor familiarization and operation a little bit, cardiovascular anatomy and physiology, electrophysiology, leads and vectors, waves, measurements, and intervals, interpretation steps, and then we're going to practice those steps on some tracings at the end. So introduction to EKGs. ECG, which EKG, by the way, that's an American thing because we have to make things hard. So the rest of the world says ECG, which makes a lot more sense, but of course we have to call it an EKG. But if we go by the way everyone else does it, which is ECG, it means electrocardiogram. And in medical terms, if we break that down, electro, right there, means electricity, cardi means heart, O is a combining vowel, and gram means to write or record. And a lot of medical words are interpreted backwards, so when you do it that way, it's a recording of the heart's electricity. So that's what that means. I don't know where the K comes from. It makes no sense, but whatever. So when do we use an EKG? Really, you can use an EKG whenever you want. There's never like a time when you shouldn't use one, but generally it's going to be like chest pain, obviously, and then like respiratory things, just because there can definitely be cardiac components with respiratory problems, so that's why we want to rule it out. So respiratory, cardiac, suspected cardiac, I should say, those are the big ones, but also like if somebody faints or if they have altered mental status, like they're unaware, just dazed or whatever, that's a good time to get one. Sometimes with chest trauma and stuff, you can get one just to see if there's anything weird going on, but really respiratory and suspected cardiac are the biggest ones, and then from there it's just based on protocol and if you feel that it's needed, really. And then what different kinds of EKGs can be obtained. So really there's two different types, technically three, but we'll discuss that maybe in probably in like later videos, or like not in this course, but I'm going to do an advanced one after this and we'll talk about it there. But really two. There's a 4-lead EKG and a 12-lead. So this course, the basic EKG interpretation, that's all based on 4-lead interpretation, and then the advanced one is 12-lead, which I'll do once I get through this one. What information can you get from an EKG? Well, you can, first of all, which we're going to do in this course, that's what this course covers, is overall heart rhythms. There's different rhythms that your heart can be in, and 4-lead EKGs are to determine what rhythm it is. Then with 12 leads, you can determine if someone's having a heart attack, if they're about to, or if they've had one in the past. You can determine electrolyte imbalances, like a condition called hyperkalemia, which is high potassium, You can see that on an EKG. You can identify hemorrhagic strokes where a blood vessel in the brain ruptured and they have increasing cranial pressure. You can identify hypothermia, pulmonary embolisms, which are blood clots in the lungs, certain conditions with electrical pathways that were or that are abnormal, that aren't usually there, that causes a different flow of electricity. Let's see. Certain cardiac medications you can identify on an EKG based on the waveforms, and you can identify cardiac tamponade, which is, we'll talk about it when we talk about the heart anatomy, but there's a protective sac around the heart, and when it gets injured or infected or something, fluid can build up in there, or blood, pus, whatever, and it's really strong, the sac, so it doesn't tear easily. So when fluid builds up between the heart and that sac, it starts to squeeze on the heart and causes issues with refilling. And you can actually identify that with an EKG as well. There's lots of things you can identify. Those are just the main things, but we'll talk about those more either later in this video or in the advanced one, the advanced EKG interpretation thing that I'm going to do. So first we're going to talk about monitor, familiarization, and operation. So we're going to go a little bit over controls, battery change, paper replacement, capabilities / features, 4-lead and 12-lead placement, and obtaining a tracing. Okay, so for 4-lead placement, which we're going to talk about here, I'm going to just real briefly go over monitor operation and stuff. I'm not going to go into it too much just because different places use different types of monitors. Like also there's Zoll, which is a company that makes EKG monitors. So this right here is a LifePak 15, and not everyone uses those. Most people do, but not everyone. So I just don't want to explain things that aren't going to be helpful to some people. And also wherever you work, they'll teach you how to use whatever monitor you have there. But just to go over it real briefly, over here is where you have your defibrillation pads, because this is also a defibrillator. So there's little patches in there that you can stick on people. Down here is where your paper is. There's a little compartment that opens up and you can put a new roll of paper in. This little cable right there, it's one of those things that goes on your finger and it determines oxygen saturation and percentage. And then it also can, at least on LifePak 15s, it can also identify carbon monoxide in the blood and percentage wise. Then there's an automated blood pressure cuff, which don't even get me started on. Here we go. I cannot stand when people only use those because they're never accurate. They're awful. Sometimes they can be kind of right, but I mean, I use one, but I only do that if I have at least gotten to manual blood pressures, because I trust my own ears more than I trust a machine, especially a machine that's always wrong. But some people, they'll just take one and they'll say, oh, if you have really high blood pressure, we need to do something about that. It's like, oh, hang on, like, did you check it manually? Because I promise you, it's probably that the machine's wrong. So for the sake of documentation and having vital signs every so often, like we're required to, I will use the automated BP cuff, but my first blood pressure and my last blood pressure are always manual. And then if I get any weird numbers in there that are just out of what I would expect based on what I got already manually, then I'll check it manually to confirm. But yeah, I don't ever just like make decisions just because of what the automated thing says. Like, always double check it manually, because they're terrible. The automated ones are terrible. I never trust them ever. So I'm going to end that rant. I could go on about that forever. Then also on this monitor, it has something called capnography, which is it's like those little nose things you put in for oxygen. And there's also one that can stick on like advanced airways, like endotracheal tubes and stuff, but it measures the air you're breathing out and measures the carbon dioxide in that air. And in turn, what it does is it tells you your body's, or the person's body, what its cellular metabolism is doing. So it's a measurement of cellular metabolism. It also displays a little waveform that's on this screen right here, and that will tell you how easily they're actually physically moving the air in and out. So like, for instance, it'll look like that, capnography waves, or it can look like that. So it'll do stuff like that, and based on that you can tell if they're moving air in and out well, and you can also tell cellular metabolism. And for someone who's experienced in reading that and understanding that, you can tell a lot of stuff for that. In fact, it's one of our requirements to be able to discontinue CPR and pronounce someone dead, is we need to be able to interpret capnography and use that, because if they're dead, they're not gonna, their cells are dying, so their cells aren't going to be functioning, and it measures carbon dioxide. So that means that if you're getting carbon dioxide, your cells are functioning, because carbon dioxide is a waste product of cellular function, or a byproduct. So you won't get carbon dioxide if your cells aren't functioning, meaning you're dead. So if you're doing CPR really well, and your CO2 or your carbon dioxide number on capnography continues to go down and it doesn't come back up, and you go for a certain amount of time without improvement or getting worse, that's a sign that they're creating less carbon dioxide, which means they're dying and it's irreversible. So we use that as one of our determining factors to pronounce someone dead and discontinue CPR per protocols. But I digress. So with a 4-lead, when you come into this little pouch, usually over here, there's going to be a cable that's connected right here directly to the monitor. On the end of that cable, you'll have these 4 wires, which people refer to as leads, but they're not technically leads. They're just electrodes, or wires is what I would call them. And even 4-lead, like it says up here, that's technically not correct. It's actually a 3-lead. But again, a lot of people call it a 4-lead, including myself, but just know that it's actually not really 4 leads, it's 3. But there are 4 wires. So these are nice because they're labeled. So RL means right leg, and RA is right arm, LA is left arm, LL is left leg. So that tells you where to put them. With these though, they're not super specific, so there's actually a pretty big area in which you can put them. So right arm can mean a pretty broad area besides like just the arm specifically, whereas 12 leads, those are very specific and you need to put them in a very exact spot. So, but these in general, it'll tell you what general area you need to put them in. One thing, just remember they're labeled because I forget. So there's a saying to remember which one goes where, and I have to say it in my head every time because I forget that it's right on the back of the thing, right here. I could just look at it and then I know, but for whatever reason I forget that, so every single time I have to say this saying in my head to remember. And the saying goes, white on right, smoke over fire. So white, which is RA, right arm, goes on the right arm, right, because right arm. So white on right, right arm, smoke over fire, because when fire burns, smoke is above it, right? So that means that the black will go above the red. So that means left arm, right? And then below your left arm is your left leg, which is this one, the red one. So smoke over fire. And then green for ground, because that's all that the green one is. It's not an actual measuring thing, it's just a ground. So you can, in theory, you could put that anywhere. You could slap it right on the center of their forehead and that would work just fine. Just for the sake of, I guess, patient dignity, you probably shouldn't do that. But we generally just put it on the left leg or the left leg's area, based on what is considered a left leg, because like I said, it can be a pretty big area that you put it on that's not exactly on the limbs, but it's called that, and you usually do put it there. So these 4 wires or electrodes are referred to as limb leads. So if someone says something about limb leads, it's going to be one of these, the right or left arm or right or left leg ones. So 12 lead ones that you actually put like along the chest Those are called precordial leads, and we'll talk about those in the next slide, but these are called limb leads. And it's white on right, smoke over fire, and ground. So now I'm going to show you where to place them. I'm going to use purple for the white one, just because you won't see white because the background of this picture is white. But basically, anywhere along here is where you can put it, the electrode. So anywhere on here, most commonly, you'll put it on the wrist for a few reasons. So right here, right in this area, and the reason for it being farther out on the limbs like that is when you do that, it's more sensitive and more accurate of a reading. However, the problem with the limbs is if somebody moves at all, it makes it just all squiggly on the monitor. So to avoid that, sometimes if you have someone that's moving around a lot or shivering or something like that, you can put it on the torso just to get a less shaky tracing, but usually we try and get them as far out on the limbs as possible just to get a more sensitive, clear tracing. So it'll usually actually go right there on the right wrist, but then the next spot you could do it, you could put it on the bicep, but or right here on the shoulder, which, you know, that's fine too, but usually it's either going to be this one right here, or it's going to be up in that area. So like just below the collarbone, before the shoulder here, so like right in this area, that's a good spot to put it if you need to put it in towards the torso. But usually, like I said, you want it out on the wrist, in this area. So then the left arm, or the smoke, black one, it's going to be, again, now we're talking about that one. Oh, it's supposed to be an arrow. This one. This same thing. You can go there, or the next most common spot is there, but it can also go there, or there, if you want it to. But this one and this one are the main ones. So there or there. And then we have fire, which is red, this one right here, and that goes on the left leg. So for this, you want to put it down kind of on the calf, like right there, even lower if you can, like maybe right there. The big thing is you want it to be over a meaty part. Don't put it over bone, because that makes it harder for it to read. And again, we want it to be farther out on the limbs for a more sensitive, accurate tracing. But if you need to, you can put it kind of like right there as well. And it can go pretty much anywhere along here as long as it's not on a bony area. But here and here especially are the main spots that we want to put it. Then with the green, which is ground, a ground lead, that one, same thing, except in theory you could put it anywhere. So like you really could just slap it on someone's forehead and it would be technically fine. I wouldn't do that probably, because, like, you know, keeping your job and stuff. So to do the morally correct thing, we just stick it right there. Makes it nice and easy, and plus it's labeled as RL for right leg, so might as well put it on the right leg. But really you could put it anywhere, because it's not actually like recording anything or monitoring anything, it's just a ground. But you can put it there, or if you need to put them on the torso, you can put it like there. So I'm going to erase all this extra stuff and I'm just going to draw it out again, but I'm going to only draw where we would normally put them. So our white one, go there. Our black one, go there. Our red one, go like there or lower. Our green one would go there. And then you'd of course have the the wires coming off of them and attached to that. So that's how we place them. These are called limb leads, if I didn't already say that. The ones for a 12 lead, those are called precordial leads, and those go on the left side of your chest in specific areas. But these ones are called limb leads. So now 12 lead placement. So with 12 leads, they're much more specific. You have to have them in an exact place because they're looking at exact areas of the heart, as opposed to a 4 lead, which is looking at the overall heart's electricity and what the overall rhythm is. So with these, we have 6 different wires or electrodes, and they're referred to as the precordial leads. And so there's V1, which means vector. V means vector, so there's vector 1, vector 2, and it goes all the way from V1 through V6. So vector 1 through vector 6. The red one, which is right here, that's V1. So V1, you're going to feel the collarbone. You're going to feel kind of the sternum, which is the bone in the center of the chest. And you're going to feel just to the side of the sternum from the collarbone. You'll feel between the ribs. It's called an intercostal space. So you'll be able to feel, then feel down, there's a rib, feel to the next space, then work your way down. You're going to go to the 4th intercostal space. So collarbone along the sternum, 1, 2, 3, 4. So it'd be right there, and it goes 4th intercostal space right to the right side of the sternum, so to the right of the sternal border. So it'd be like right there, and that would be V1. Then our yellow one, that is going to go in the same spot except on the left side. So the left side of the sternum, 4th intercostal space. So right there. And again, that's V2. Then we're actually going to skip V3 and go to V4. And you'll see why in a second. But V4 goes mid-clavicular line, which is basically that little indentation like halfway from the end of your shoulder to right about the center of your chest. There's like that little part right there. That's called your mid-clavicular line. So you're going to come 4th intercostal space, 1, 2, 3, 4, and you're going to come, or I'm sorry, you're going to go 5th intercostal space, so one more down from where V1 and V2 are, and you're going to come over till you're in line with that mid-clavicular line. So 5th intercostal space, mid-clavicular line, that's where V4 goes. So that would be, where is it? The blue one, so it'd be like right about there. And that is V4. And then we go back to V3. Excuse me. V3 is going to be between V4 gosh, between V4 and V2. And that'll be the green one. So just perfectly right between V1 and V4. Then we're going to skip V5 and go to V6, and V6 is going to go 5th intercostal space, mid-axillary line. So basically right where the armpit is in the middle, straight down on on the 5th intercostal space for V6, and V6 is purple. So that'd be like all the way over there, kind of hard to see at that angle. V6, and then we come back to V5, and it's just like with V3, it's going to be between V6 and V4. And that's like a orangish color, which I don't have an orangish color here for demonstration. So we're just going to use a black one and pretend it's orange. So it'll be right there. 5. And then I should probably write the V3 in. There. So that's where those go. So again, to recap, V1, fourth intercostal space, right side of the sternal border. V2, same place, left side of the sternal border. V4, fifth intercostal space, mid-clavicular line. V3, between V2 and V4. V6, fifth intercostal space, mid-axillary line. V5, between V6 and V4. Then when you actually go to get the tracing, there's a little button that is over on the left side of the monitor right here that says 12 lead. Before you hit that though, because it'll start analyzing like as soon as you do that almost, you want to watch the screen here, because whenever someone moves, it's going to make it kind of all jumbly. So first thing you want to do, you want your patient to hold really still. They can breathe normally, but if they move or talk, it's going to mess it up and give us what is called artifact, which we'll probably talk about later in this video, but it's just noise, like just chaos that doesn't mean anything. But I always say the same thing to every patient, so that way I don't forget to say it and I remember everything to say for instruction wise while we get a 12 lead. I say, okay, so we're going to take a picture of your heart. What I need you to do is hold really still. You can breathe normally, but don't move or talk until I say so, so that way our monitor can get a clear picture of your heart. And usually, like, as soon as you say that, they'll just start moving and coughing and doing whatever. It's like the second, they'll be still the whole time. The second you tell them to stay still and not move or talk, then all of a sudden. And one of the most common things, kind of pause for a second after you say that, because usually you'll go, after you say, hold still, you know, so we can get a picture, okay? And they'll say, okay. It's like, well, that just messed it up. So give them a second, because they'll probably say okay, and then wait for it to go normal and then push the button. But yeah, that's just how it is. Like, someone will be still like this, and then you tell them to hold still and breathe normally, and as soon as you hit the 12 lead button, they go, oh man, they start like wiggling around and stuff. I don't know what it is, but that's something you can expect. Anyways, so wait till it's clear. Make sure you tell them to hold still, don't move or talk until you say so. That's also important to say that. Hit the 12 lead button, a little screen will pop up here, and it will say, or I'll ask you to select male or female, and then with this dial you'll input the patient's age. You just turn the dial to whatever age, and then you push the center thing, and then you just leave it. It'll take a few seconds, and then it'll just automatically print out a 12 lead right there. Sometimes it thinks that there's noisy data, as it's called, which means they're moving around, or the machine thinks it's not clear enough. And you can either wait and it'll get it once it is clear enough, or you can just override it by hitting 12 lead. The only thing is, when you do that, it usually on the paper it says, it gives an interpretation. It'll say what it thinks is wrong, like what it found, and it won't do that if you override it by hitting 12 lead, but that's okay, because you should never go off of what the machine says alone. Treat your patient, not your monitor. And you can use the interpretation on the monitor to kind of just double check and confirm if it's what you saw, but never go solely based off of what the machine says, just like with the automated blood pressures. So hitting 12 lead to override it's not a big deal, because you shouldn't be using the monitor for interpretation anyways. It's just nice sometimes to have that little extra confirmation, but either way, so once that prints out, then you got your 12 lead and you're good. So, and you do have to attach this to the 4 lead cable, because these don't come attached, they're just wrapped up like this and put away in a pocket somewhere. But yeah, so that's how you obtain a 12 lead. So now we're going to talk about cardiovascular anatomy and physiology. So we're going to discuss what is the heart's job. We're going to talk about the chambers of the heart, blood vessels, anatomical structures of the heart, coronary blood supply, and blood flow through the entire cardiovascular system. So to start off on what the heart's job is, the heart is an organ, and it's a muscle. That's the type of organ. It's a muscle. And its whole job is to just pump. It fills with blood, and then it beats, which pumps blood out of the heart and circulates it throughout the body. So that's all it is. It's a muscle that pumps blood. It's a pump. And the reason that's important to circulate blood is because blood carries oxygen, which is what our cells need. It also carries our nutrients, water, all that stuff. So without going into this too much, because it's related and important, but it's slightly off topic, cells are microscopic versions of us. So we're just a cluster of cells together, and we're so many microscopic things put together that we're actually visible, basically. So that's how many cells we have in our body. But our cells are little tiny microscopic versions of us, so they require all the same things that we do in order to stay alive. So they need food, water, and oxygen, all of which are circulated to them by the blood. So those nutrients, that oxygen, that water, gets into the bloodstream, it gets to where it needs to go, it goes out of the bloodstream into your cells. Your cells use that oxygen to turn your food into ATP, or adenosine triphosphate, which is the body's form of energy. And then that energy allows the cell to perform its specialized function and stay alive. So uses oxygen to turn food into energy. As a byproduct, sort of like a car has exhaust, your cells create carbon dioxide, which is its waste from that process. That waste then needs to get taken back into the bloodstream and circulated through your body, and it'll go to your lungs, the CO2 will, carbon dioxide, and you will then exhale that. So that's how we get it out of our body. So that's why blood flow is so important, because it gets the stuff to our cells that they need in order to do their specialized function and stay alive. So if we can't get that to the cell will eventually die. Likewise, if we can't get rid of waste products from your cell functioning, that will also cause problems, which can cause death as well. So it's very important to have circulating blood to get the good stuff in and the bad stuff out. So next we're going to talk about chambers of the heart. So as I mentioned, the heart is a muscle, and within this muscle there are 4 areas that are hollow, like collection areas, or just pockets, just opening areas. So the heart is fully enclosed, like blood vessels come out and come back in, but there's no like actual opening, it's all sealed. But there are hollow sections, so here, 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 and here, and those are referred to as chambers. We have 2 lower chambers, which are both called ventricles. So this would be your right ventricle, this would be your left ventricle. Now, ventricles are the actual pumps of the heart. Their job is to pump blood out of the heart. So the right ventricle, it pumps after the chamber fills with blood. The right ventricle will pump, and it'll pump blood out to the lungs so they can get oxygen. Because when we breathe oxygen in, it goes directly through our lung tissue, like the walls of our lungs, and absorbs directly into our bloodstream. So carbon dioxide also gets out that way. It gets circulated from our cells after that process of function. It comes back into the heart, and then when it gets pumped to the lungs, it just kind of seeps through the walls of your lungs, fills your lungs, and you exhale that. So the right side of the heart pumps blood to the lungs. Then the left ventricle pumps blood to the body. So this one is going to be more muscular, and it's going to beat harder because it has to get blood throughout the whole body, whereas the right ventricle only needs to get blood to the lungs, which are like right there next to it. So a lot more force in the left ventricle. Then our 2 upper chambers are called atria, which sort of like an atrium in a building. It's like an area, like a commons area or something that people can hang out. That's how you can think of the right atrium and left atrium. It's just collection points. They do pump, but that's not their main job. So blood will come in, and also just to clarify, it's better to think of the heart as being divided right and left instead of top to bottom. And as I go through this explanation, you'll kind of see why, but blood will always come into the heart, into an atrium. It'll collect there, and then once the heart beats at the proper time, a little door or valve will open, and the blood will just drain down into the ventricle directly below it. Then there's a little impulse that comes through the atrium, and it causes a small contraction, which just pushes extra blood that might be in there out. That's called atrial kick, that kind of final contraction of the atria that gets the rest of the blood down into the ventricle. Then once the heart beats again, the ventricles will, like I said, pump it out to either the lungs or the body. And then in the lungs, once that carbon dioxide gets out and you breathe it out and the oxygen you inhaled gets absorbed into your bloodstream, that blood then comes back into the left atrium where it collects. At the right time of the heartbeat, a valve will open, that blood will just drain down into the left ventricle. Then, when it beats again, it'll pump that blood with fresh oxygen throughout the body. So again, think of the heart as left and right. Each side has an atrium and a ventricle. The atrium is a collection point that collects blood that comes to the heart. Then, at the proper time, the blood will drain down into the ventricles. There will be a small contraction of the atria, which will get the rest of the blood out and down into the ventricles, and that's called atrial kick. Then the ventricles will pump, and the right ventricle will pump to the lungs, the left ventricle will pump to the body. Alright, so this is kind of along with what I was saying about the fresh oxygenated blood, or the fresh oxygen in the blood coming back to the heart, and the carbon dioxide that's in the blood going to the lungs to be exhaled. The two terms we use are deoxygenated blood and oxygenated blood. So deoxygenated blood is blood that is low in oxygen and high in carbon dioxide from cellular metabolism. So basically anything coming from the body to the heart is going to be deoxygenated because that's all the blood that contains the carbon dioxide from your cells doing their thing. So in this picture and in every picture you see in any textbook or anything, there will be parts that are colored blue, and that represents deoxygenated blood. So there's this big vessel, and there's one down here that comes up, and they come in through here and there. So that's blood from the body that's deoxygenated, so high in carbon dioxide. It comes from the body, fills the right atrium, then, like I said before, at the proper time a valve opens, falls down into the right ventricle. Then when the heart beats again, it'll come up and out this way, as well as behind this red thing and out that way, which goes to the lungs. In the lungs, the carbon dioxide fills your lungs, goes out of the bloodstream to fill your lungs, and then you exhale that. When you take a breath in, that fresh oxygen absorbs through the walls of your lungs into your bloodstream. That is then oxygenated blood because it's high in oxygen, low in carbon dioxide. That blood, the oxygenated blood, will come back to the heart and fill the left atrium. Then when the heart beats, valve opens, it drains down into the left ventricle. When the heart beats again, it'll come up through this right here, behind this blue one, up, around, and down, or up and through these to your upper body. And that's going to be oxygenated blood. So fresh oxygen, which will then go to your cells. It'll leave the bloodstream, get into your cells. Your cells will use that oxygen to turn food it gets into energy to perform its functions and stay alive. And then it'll create carbon dioxide as a byproduct, which will get absorbed back into the bloodstream, travel back to the heart, into the right atrium, and that process starts over, and it just circulates like that. And then so we're going to talk a little bit about blood vessels here. There's an arterial side and a venous side. So arteries go away from the heart, and an easy way to remember that is because artery starts with an A and away starts with an A. So so arteries go away from the heart, so it's all the blood leaving the heart. and then veins are going to go to the heart. So all arteries, with one exception, have oxygenated blood because they're leaving the heart. It's pumping blood out to the body, so that's fresh oxygen. One exception, which we'll talk about once we talk about structures, is the pulmonary vein, or I'm sorry, pulmonary artery. And once we go over structures of the heart and everything, we'll talk about that more, so don't worry about that. But in general, arteries carry oxygenated blood. So I listed them from biggest to smallest. So the first biggest vessel, which is the one that comes directly out of the left ventricle, that's called your aorta. And then that will slowly branch off into arteries. Then at the smaller level, it'll branch off into arterioles. Then at a microscopic level, it'll be capillaries. And when I say microscopic, I mean it's so small that all your blood cells, they can only go through there in a single file line because they're so narrow. So that's capillaries. And I put it also up here on the venous side, and on the venous side it goes from smallest to largest. The reason I have it on both is because capillaries aren't really an artery or a vein. It's kind of a transition from one to back into the other, and there's no specific point at which it changes from artery to vein or from vein to artery, either way. So I have them on both, but that's the level where the gas exchange occurs. So that's where the oxygen leaves to go into your cells, and that's where the carbon dioxide comes back into your blood, is at the capillary level. From the capillaries, it'll slowly kind of come together to form venules. Then that will come together to form veins. And then lastly, the vena cava, which is the big vein that comes through the bottom and the top of your heart into your right atrium. So this is just kind of to show how it works, so that there is no end to your blood vessels. It's just a continuous loop. It just comes out like this, slowly branches into smaller things, and at the capillary level, it's like a net, sort of like this, just a net across everywhere in your body. That's where the gas exchange occurs, then it comes back in, it goes back there, and it goes to your lungs, and in your lungs you also have pulmonary capillaries, so you also have that same net of microscopic blood vessels for gas exchange. And let's see here. Yeah, so I'll just quickly draw it just to kind of discuss it a little bit. So in here, whoops. So your cells are just clumped together like this, all in your body with veins running through. The white space in between is something called interstitial space, which is just filled with fluid, and that's why we are mostly water. It's because it's like putting marbles in a jar. If you were to do that, the jar itself would be like your skin or your outer barrier. The marbles would be your cells. And then if you imagine, because of their shape, there's going to be space between all those marbles that are in the jar, so that you could fill with water. And that's how our body is. So that space where the water is, that is called interstitial space, and that is why we are mostly water. But the cells are all clumped together. I'm going to draw one down here just to make it bigger so you can see. So if that's a cell, we have oxygen, O2, coming down this way. Once it comes down this way, through this network of capillaries, it will come out of the bloodstream through the interstitial space into the cell right here. The cell will create energy, then it will create carbon dioxide, CO2, as a byproduct, which will leave the cell, go into the interstitial space. That's a horrible arrow. And then it'll get absorbed back into this bloodstream, and it'll go all the way back up here to the right atrium, to the right ventricle, get pumped to the lungs, and it's deoxygenated blood, as I mentioned before. Then the same process occurs. It'll go across the walls, fill the lungs. You will exhale that carbon dioxide. Then you will inhale fresh oxygen, which will fill your lungs, and it will go across the walls of your lungs into your bloodstream, get returned to the left atrium, then down to the left ventricle, then get pumped out to your body like that. And the process just continues like that, non-stop, until we die. So same thing, this is at the capillary levels. These are arterioles, these are venules, and then these are capillaries in here. So you'd have like cells all in here, and there. So let's see here. Just draw one right here. So again, O2 would come in here, come down this way, then right here it would come out of the cell, out of the blood vessel into this cell right here. Cell would use it to perform its function, stay alive, and it would create carbon dioxide as a byproduct, which would then come back in here through the venules and capillaries and stuff, and then it would get pumped back up that way, back to your heart, then to your lungs, so you'd exhale. Alright, so anatomical structures of the heart. Mainly what we're going to talk about, real quick just to go over it, how I said all arteries, or all except for one artery, are deoxygenated, or geez, all arteries except for one are oxygenated, yeah. That would be the pulmonary artery, which is this one. Because again, an artery is anything that goes out of the heart, that blood travels out of the heart from. So technically, this right here, when it beats and sends, God, I don't know why my voice is all messed up now. When it goes out of here to your lungs to get oxygenated, that would count as an artery because it's going out of the heart, but it's carrying deoxygenated blood because it came from the right atrium, which gets blood from your body. So that's the only artery that's deoxygenated. Likewise, there are only some veins that are oxygenated, and that would be the pulmonary veins. So there's two on each side that bring blood back from the lungs that has oxygen that was just inhaled. So those are the only veins that are oxygenated. So then the big one for us in EKG related things is this right here, which is called the interventricular septum, or just the septum, as a lot of people will call it. And that's just muscle there, like everything else in the heart is, but that's what divides right and left, specifically right and left ventricles. There's also a separator up here kind of the atria, but mostly it's going to be dividing the ventricles. And then along here is just more heart muscle, which in medical terms that would be called myocardium. Again, to break down the medical word, cardi, heart, my means muscle, so myocardium is heart muscle. Then we have valves. The way these valves work in the atria, they're a little flap that has kind of a lot of tension, so they just snap shut whenever they're pulled down like that. There's little tendons that attach to it and then attach to the wall down here within the ventricles. And what it'll do is at the proper time, they're only a certain length, those will tug and it'll pull the flap down or the valve down, which will allow blood to drain. Then once contractions stop or whatever's pulling on it, there will be no more tension, so it'll just snap shut. And that'll stop blood flow from going back into the atria. Then out of the ventricles, we have these little W-shaped things. So they're like this, or I'll do it like that. And it's the shape of those that makes them work. So when the heart pumps, it causes pressure, which will push the blood up and through. So it'll be like this, and it'll open up because blood's pushing up, like up on it, like, yeah, you get it. So it'll push up, open them up, and then once that surge of blood from the heart beating stops, gravity-wise, it'll cause blood to fall back down. And if you look right here at the shape of them, right here in the center, that's where it opens up at. It comes together at the top here. But this creates a U shape on either side. And that is what closes it, because the heart pumps, the blood comes up, but then once it starts to fall back down, it gets kind of pooled in these U shapes. And what that does is it actually pulls it back together. So it pumps, blood comes back, it'll collect on this side and on that side, which will push it back shut. And those valves are what allow blood to flow in one direction and not go the wrong way and mess everything up. So we got the tricuspid valve here from the right atrium to the right ventricle, then going to the lungs out of the pulmonary artery, we have the pulmonary artery, or the pulmonic valve, pulmonary valve, whatever. Then coming back in, and between the left atrium and left ventricle, we have the mitral valve. Then we have the aortic valve, because this big blood vessel right here, again, is called your aorta. And then for both the atria, there is no valve, just blood continuously comes in and fills it. So from here, from the top, the superior vena cava, it's called, just pours in. The inferior one pours in, although there are some of these valves similar to the tricuspid and mitral valve, I'm sorry, the pulmonary and the aortic valve that have that same shape, so that pulls them shut, because veins, you know, with gravity, they pump up a lot, so it's hard to keep blood going in one direction without those. But at the actual heart itself, there is no valve in the atria for blood coming into the heart, only between chambers and vessels going out of the heart. And a good way to remember which is on the right and left as far as tricuspid and mitral, the saying that someone told me once was, try to do right. So tri as in tricuspid, to do right, right as in right side. So try to do right means the tricuspid valve is on the right side. So then obviously you'll know the mitral is on the left. So coronary blood supply. Just like everywhere else in our body, our heart needs oxygen. Breathing, by the way. I was doing good so far, but it's needed now. So we have what's called coronary blood supply, and that's our blood vessels that go to our actual heart muscle, the myocardium, and get the individual cells, which are called myocytes. Site means cell in medical terms, so muscle cells, myocytes. It gives them the blood that they, or the oxygen that they need, and blood. So the way they work, this is a front view of the heart, and over here is a view from behind the heart. But we have on the left side, we have this right here, which is called our left main coronary artery, or LCMA, or LMCA. And that goes into the anterior descending. And then there's one called circumflex. And then we have the, I believe this is the marginal as well. I don't know. But yeah, so it'll come this way and get the left side of the heart. Then we have our right coronary artery, which comes down here. And again, they just branch off into little things, so they're at a capillary level. So they just spread out, and then they come back through veins, which come up in this area. So this is like our carotid sinus, or coronary sinus, sorry. And then we have our right coronary and our left marginal artery and vein. And these all come back, and they go directly into the right atrium to be oxygenated and circulated again. So these are the richest oxygen supply we have in our blood, because they're attached right here, and then this one comes behind this pulmonary artery, the blue one, and it attaches right over here. So it's directly at where the blood comes out of the heart, that's where the supply comes from. So it's the richest supply of oxygen, and that's because our heart really needs oxygen, because it's very important to not die. So the way the circulation works is it's not the initial surge of blood through this artery that causes it to fill with blood or to circulate blood to the heart. It's something called retrograde circulation. So in the same way that after the heart beats and the blood starts to fall down, it pulls those valves shut. That same thing allows blood to come down into these blood vessels of the heart. So it goes up, and then after that beat, it slowly comes down, and there's no valve or anything to the coronary vessels. So instead, when the blood comes up, it comes back down, and as it comes down, it just circulates through these and fills the heart muscle or the heart vessels with blood, or circulates new blood in, I should say, because they're always full. And then, yeah, that same process with the oxygen and carbon dioxide goes on, comes back to the right atrium, then right ventricle to the lungs to get rid of carbon dioxide, bring fresh oxygen in. But again, the circulation, or how it gets circulation, is something called retrograde circulation. And these vessels, they're not super important for 4 leads, so this is about all that we're going to talk about them. But when I do my advanced EKG course thing on here, that's going to come in handy for determining where heart attacks are. Because when you get a 12-lead EKG, not only can you identify that there is a heart attack, but you can identify the exact area and the exact vessel. So if there were, say, a blockage right here, it would affect like this whole area in here, and on a 12-lead EKG you would see that, and that's called the left anterior descending. So you could see on the EKG they're having a heart attack, and based on where you see that, you could say they probably have an occluded left anterior descending artery. So when I do that course, we'll discuss how to do that and how to determine which vessel it is, but just a little fun thing to know until then. So this one, we're not really going to go over this too much because this is literally what we've been talking about the whole time, just getting oxygen in and carbon dioxide out. What I will discuss very, very briefly is how. So something called diffusion. So when you breathe in, you've got this fresh oxygen, it comes to the end of your lungs and fills these little ball-like things called alveoli. It'll fill those, and they're only a cell thick, so it's easy for stuff to get in and out. And the way gases work in our body is by something called diffusion. So they move from an area of low concentration to high concentration because oxygen, it's a molecule and therefore has atoms in it, and atoms are moving. They're constantly in motion because they have something called a valence shell with electrons. You don't need to worry about that, but they're always moving. So everything has vibrations to it and whatnot. So what happens is when you have a gas that's like oxygen coming in, all those oxygen molecules are very close together, and since they're always moving, that causes them to bounce into each other, and when they hit each other, they kind of bounce away like that. So if you have this huge cloud of a certain molecule and all these little things, they just bounce into each other, and that causes them to slowly separate. They'll slowly spread away as they bounce into each other. They'll get more distance, might bounce into each other again until they're equal distance, and it's equalized. So that is what causes diffusion, which is it moving from an area of high concentration to an area of low concentration, or down its concentration gradient. So diffusion, those molecules, oxygen molecules within the alveoli hitting each other, causes them to spread out, and then they seep through the walls of the alveoli into the capillaries, where they attach to red blood cells and get circulated to the body, and then we know the process from there because I've been talking about it over and over during this video. But yep, it goes out of the heart, boom, to the cells use it, carbon dioxide is made, back to here, boom, to the lungs, fills the alveoli by diffusion again, and that then gets exhaled. So now we're going to talk about electrophysiology. So this is, at least part of this is kind of the harder thing in my opinion, one of the harder things. But I'll try not to make it too confusing. But we're going to talk about the cardiac conduction system, action potentials, cardiac myocytes and automaticity, pacemakers and inherent rates, and ectopy and irritability/escape. So the cardiac conduction system. Our heart, it beats by electrical impulses, which you can refer to those as an action potential. Like in a single cell, it's called an action potential. And then the overall contraction or stimulation of a cell we refer to as depolarization. And then as it gets back to its state where it can contract again, we call that repolarization. When it's in a ready state, ready to contract, it's called polarized. And that also is going to be discussed more, but just for a brief overview. So within our heart, we have a really dense node of a special type of cell called conducting cells, or I'm sorry, pacemaker cells, which generate the impulse. And that'll be up in here, and I'll draw that in with, use green. So like right up in here, there's this really dense node made up of pacemaker cells, which generate an impulse. And I'm going to just number this instead of trying to write out the whole word, because with my little mouse pad thingy here, it's a little hard. But this, number 1, which is, put it over here too, number 1. So that would be the sinoatrial node, or the SA node. So it's commonly referred to as the sinus node, sinoatrial node, or SA node, usually SA node. And that's found up in the right atria, and that's where the impulse is created, and then from there it gets sent down through the atria. So there's one little wire, as you can think of it, that goes over to the left atria, and there's one that comes this way, and one that comes down the middle there. And as the impulse travels down this wire, it spreads out to the individual cells. Those cells then depolarize, which is contract, and then that causes the neighboring cells to depolarize, and then those neighboring ones to depolarize, so it just kind of spreads like that through the atria, which causes atrial contraction, also known as atrial kick, which is that final last little contraction to get the remainder of the blood in there down into the ventricles. So these pathways right here, I'm going to use a different color just so it's not confusing. So this one, and this one over here, those are going to be number 2, and number 2 is called the internodal pathways. So that's what goes through the wires that run through the atria. Then we have right about here-ish, we have another node of dense cells. And these ones, the way it works is they're actually like interwoven, like mesh-like cells, or fiber like that. And it's so interwoven and dense that it causes resistance. So when the impulse comes through really quick, it gets to that node and it kind of has to force its way through, which slows it down for a second. So it'll go through the atria really quick and then slow. It'll come through the atria, slow, and then once it gets through, it takes off again. And this node right here is called the atrioventricular node, or AV node. And that makes sense because atrioventricular is between the atria and the ventricles. Atrioventricular. And this will be number 3 over here. So AV node, atrioventricular. So that slowing of it, the impulse as it goes through that node, the AV node, that allows for the atria to finish contracting and finish getting that extra blood down into the ventricles. Then from there, it'll go out of the AV node through this thicker electrical pathway that crosses over here. And this pathway, number 4, is called the bundle of His. The bundle of His will then, right around here, divide into 2 separate branches like this, and these are called bundle branches. So 5. So bundle branches, there's a right and left bundle branch, and then each one will then go up the side of the heart like this, and it'll just kind of spread through various pathways and to all the individual cells of the ventricles. And these little fibers here are called the Purkinje fibers. So again, just to recap that, the sinoatrial node, or SA node, is a dense node of pacemaker cells which generate an electrical impulse. They then send that through these pathways called the internodal pathways through the atria, which causes the impulse to spread out to all the individual cells and causes atrial depolarization or contraction. That impulse then comes to the atrioventricular node, also called the AV node. Its density causes the impulse to slow and get the remaining blood down into the ventricles. It then goes down the bundle of His, divides into the right and left bundle branch, goes up the sides and through the Purkinje fibers to the individual cells of the ventricles, and then they depolarize and contract. And one thing to mention also is that between the atria and the ventricles, oops, I meant to do that in red. Between the atria and ventricles, there's this wall of tissue that is non-conductive. So that means an impulse cannot travel through it, and that's really important for keeping an organized beating where the atria and ventricles aren't trying to beat at the same time, or there's not impulses coming from random directions, because otherwise it could come like down here and up there at the same time that it's coming this way, and then it gets all disorganized. So there's a non-conductive wall there that keeps the impulses separated. It keeps anything going on in the atria going on up there, and then once it goes down to the ventricles, it's only down there, and it's not affecting the atria. And in the advanced EKG class, the 12-lead one, we're going to talk about a condition called Wolff-Parkinson-White, WPW, which is where you have an accessory pathway. So you're born with this extra little pathway, like anywhere, it can be anywhere in there, but say like there, for example, and that'll actually allow impulses through. And again, we're not going to get into that in this video, but that can cause a bunch of issues with directional flow of electricity and result in some medical emergencies. This is just other pictures that are better than my cute little drawing I did, just because I wanted to have a more clear picture so you understood. But up here, this is the SA node, internodal pathways right here, there, there. That wall is right along here, that non-conductive wall. Right here is the AV node, bundle of His, left bundle branch, right bundle branch, comes up through here and spreads all in here and there, which are the Purkinje fibers. And then over here is just another example again. SA node, internodal pathways, AV node, bundle of His, left bundle, right bundle, Purkinje fibers. So now we're going to talk about an action potential, which is the actual electrical impulse that goes through all the cells, because even the pathways and the nodes are made up of single cells just clustered together. So each individual cell, whether it be a cardiac myocyte, a heart muscle cell, a pacemaker cell, or a conducting cell, they have action potentials, which is what causes or transmits the electrical impulse. So all that it is, those electrical impulses, is it's a shift of electrolytes, because we have electrolytes that are outside of the cell and some that are inside. So when they shift and cause a change in positivity and negativity between the outside and inside of the cell, that causes depolarization or contraction of the heart, and therefore an impulse to be generated or conducted. So the main electrolytes that our body uses for action potentials would be potassium, sodium, and calcium. And then we've already talked about these, the pacemaker cells and conduction cells. So first we're going to talk about an action potential within a pacemaker cell. So just check my notes, make sure I don't miss anything. So these cells are the ones that are usually responsible for initiating a heartbeat, because that's ultimately what an action potential does. As it spreads through the heart, the end result is a single heartbeat. So, 1 second here. So when our heart muscle is, or our heart cells, any type of cell, is in a ready to contract or ready to transmit or generate an electrical impulse, it's called polarized again. So when our cells are in a polarized state, the inside of the cell tends to be more negative than the outside of the cell. So in this picture, down here is inside the cell, and out here is outside the cell. These little things right here are called phospholipids, and they make up something called the phospholipid bilayer. It's actually one little like spear, like ball thing with two little prong-like thingies coming off of it, and then it just looks like one continuous one because they're flipped facing each other like that. And that's what creates the wall of our cells. So this is our cell wall. And just an interesting fact, these little heads here, they're called hydrophilic, which means they like water, while these lipid tails are called hydrophobic, so they don't like water. So naturally, the hydrophobic lipid tails will try and face away from water, while the heads, phosphate heads, will try and face or turn in towards water because they like water. So since the inside of our cell is water, and the interstitial space, which is the space between cells, since that's water, that means we have water inside and outside. So therefore those lipid tails, they turn towards each other like this because they don't like water. So these guys like water, so they face outwards to the outside water. These guys face inwards to the inside water. And these guys point to each other to keep this area as water-free as possible because they don't like water. And that's what creates our cell wall. Then we have large proteins within our cell wall, which create things called channels or gates. And that's what allows certain things to pass into the cell and certain things to exit the cell. The cell wall, or cell membrane, also called phospholipid bilayer, is made up of, or it's considered a semi-permeable membrane, meaning it allows certain things to pass in and go out, like I just said. The reason it's semi-permeable is because some things can just float right between these phospholipid things right here and go into the cell, some can flow freely out, while others have to go through these protein channels. So that either something has to stimulate the channel to open and let them in, or it'll just naturally let them in at a slower rate, or there's different ways that they can work, but that's what makes it semi-permeable. The main channels for action potential, we're going to have this first one, this first one here is going to be a sodium channel. And then we have a calcium channel, potassium channel, and this is called an AT-PACE pump, or sodium potassium pump, whatever. So in a polarized state, I'm just going to draw how that would look. In a polarized state, we have not a lot, but some potassium within the cell, like this. Then we have much more sodium and calcium outside of the cell. in a polarized state, that is. So a state where it's ready to depolarize or ready to cause a contraction and generate or conduct an electrical impulse. So we have all this sodium out there. We also have all this calcium out here. And this is the part that kind of confuses people, because all of these electrolytes, by the way, they're called ions, which are electrically charged particles. All of these ions that make up these electrolytes are something called cations. So a cation is an ion that carries a positive charge. And a good way to remember that is the word cat has a T in it. Same with cation, and it's like a positive symbol. So cations are positive, whereas anions are negative. And in anions, there's an I, which if you turn it to the side, looks like a minus symbol, like negative. So our body uses for action potentials in the cardiac cycle, it uses all cations, which all have positive charges. So that confuses people when you tell them that the inside of the cell is more negative than the outside. And the reason we say it's more negative is because if you look out here, we have 1, 2, 3, 4, 5, 6, 7, 8, and those actually carry a double charge. So it would be 2, 4, 6, 8, 9, 10, 11, 12 cations or positive charges outside of the cell, and we have 3 positive charges inside. So even though there's positive on both sides, it's more negative in here than it is out there, if that makes sense. So that's a polarized state ready to depolarize. In a pacemaker cell, we have these little guys right here, which are sometimes sodium channels in the next example we're going to go over, but in pacemaker cells, they're called funny channels, which I was trying to think of a joke, and I couldn't think of one. I was going to say something about the humorous there, and be like, that's not very humorous, but these are funny. I don't know, like, you can probably just turn the video off now. I'd be done if I were you. That was stupid. Anyways, these funny channels, there I go with the joke scene, doesn't matter. So they'll open and they'll allow a slow influx, which means pouring in or inward movement of sodium. So there's an influx, an inward movement of sodium into the cell. So this all starts to slowly come in. Now, for an action potential, what happens is we don't want to just have any stimulation or any sort of anything happen and trigger an action potential, because then everything in our body would be overactive. So instead, our individual cells, they have a threshold. So that's a level at which they need to reach in order to trigger an action potential in that whole process. So at, let's see, is it on here? Yeah. So usually like negative 40 millivolts is what it is. So right now the inside of the cell is way below that, but as we have this slow influx of sodium, it starts to rise, and once it hits negative 40 millivolts, that triggers an action potential, and the electrical impulse is generated or conducted. So that slow influx brings it up to threshold, triggers the action potential, and when that happens, we have these calcium channels open, and calcium then pours into the cell. So with that influx of calcium, we have an even larger increase in positivity. Then, at a certain point, we're going to have the calcium channels close, and then we're going to have this, which is a potassium channel. It's going to open, because there's usually a gate there. It'll open, and it'll allow potassium to leak out, or in other words, it would be an efflux of potassium, exit of potassium. And that'll cause a drop in positivity, and that'll cause it to come back to a more negative level. and then eventually down to its resting or polarized state. And then this right here, the AT pace, it'll just pump the remaining electrons or the remaining electrolytes in and out of the cell to kind of equal things out. So this one will bring potassium back into the cell. This one right here will get rid of excess sodium. So that just switches things back to their normal state, resting polarized state. So again, these little dots up here I was going to show step by step, but that's like what I just explained, so I'm not really gonna do that right. Well, I guess I kind of will. So first we have influx, slow influx of sodium through the funny channels. Then we have shortly after an influx of calcium through calcium channels. Then once those close, we have an efflux of potassium, and eventually we have the efflux of sodium and influx of potassium, which returns everything to its polarized state. Now, to discuss that threshold I was talking about, we're going to look at this little graph over here. So this way equals time. This is voltage in millivolts. So if our threshold, where did I go? There we go. So if our threshold of negative 40 millivolts is like right here, negative 40, as those funny channels open up and there's a slow influx of sodium, it starts to rise. Rises, rises, rises. Once it hits here, which is the threshold, that triggers an action potential. When the calcium channels open, there's a rapid influx of positivity, so it'll just shoot this way up. Then once those channels close and potassium opens, it causes this little decrease, and then eventually it'll equal out as it's moving things around, and then it'll cause a little plateau, kind of. Not so much in pacemaker cells, but it'll mostly just kind of go straight down, but in conducting cells there will be a plateau. And then eventually the AT pace will swap things around and it'll come back down to its polarized resting state. So now for conduction cells, we have a different process. So these are stimulated mostly by neighboring cells. So when that action potential occurs in the pacemaker cells, like we just saw, that shift in electrolytes, it causes electrolytes to flow into neighboring cells, which then increases their positivity. So when they get stimulated, that will also cause their positivity to increase, and then they will hit their threshold. When that happens, fast sodium channels open. There's a rapid influx of sodium. Shortly after they open, there is slow calcium channels that open, and then there's a slow influx of that calcium, which further rises the positivity. And then eventually those will close, or the sodium channel will close. The calcium channel will stay open, but it's slow influx, remember that. Meanwhile, potassium is still leaking out of the cell, which it does. And then what that'll do is it'll cause that drop like we were talking about in positivity, but we still have some calcium going in, some going out. Eventually they'll equalize, and the inside and outside will be equal in positivity, or polarity, as you can call it. And then those calcium channels will close. And, sorry, my dog's making weird noises. Blue. Stop. And then the AT pace the AT paste will swap things around, so it'll get rid of that extra sodium, and it'll bring that potassium back in and return it to a polarized state. And the calcium, we're not going to talk about that right now, but the calcium gets moved around by a different method. So I didn't talk about this in the last video, or I'm sorry, the last slide, but I'll mention it here. There's phases to the action potential. Whoops, that's a terrible threshold, but -40. So we have that stimulation by a neighboring cell brings it up. Once it hits -40, action potential is triggered, starts the rapid influx of sodium right around here, followed by calcium, comes up, and then those channels close, or at least the sodium channel closes, calcium stays open. Potassium, let's see, I should have drawn this in up here as I was going. So this right here is called phase 0. So I'll write it up here. 0 is going to be basically the stimulation or the efflux of potassium, which is caused by the stimulation. Then from there, as the sodium channels open, fast sodium channels, that would be called phase 1. And I also have calcium. Then, once the sodium channels close, there's still calcium coming in. Blue! Damn it. Still calcium coming in, which causes, which causes phase 2, which is this decrease. It then goes to the blue, shut up. It goes to the plateau. 2. Stop. Come here. Sit. It's fine. So then at that plateau phase, there's still rapid or slow influx of calcium, but there's also still potassium leaking out, so that causes it to equal out. So that's this plateau. Then once the AT pace pump pumps sodium out and potassium in, that's what will rapidly bring it back down to its resting potential. So go 1, 2, I think that's 3, and then 0, back to phase 0. So that's important to understand, but like you don't really need to understand it, at least for this, the basic EKG interpretation. You don't need to understand the process in extreme detail, but you do need to get the general idea of it at least. So cardiac myocytes and automaticity. So these are your muscle cells. Where these little suture-looking things are, there's something called blue. Come here. Come here. Stop barking. There's these little gates called desmosomes, and that's where the electrolytes will come out from the action potential of one cell, come into another cell, and cause that increase, which stimulates an action potential. Then we have these little things right here, which kind of like interlock like that, and it holds the cells together. And then the cells themselves are also that way, so they can stretch, and that allows for more contractility. So it's like the example I heard was if you blow up a balloon and then let the air out, if you blow it up a lot, it stretches more, which forces it out quicker. If you blow it up a little, it's kind of a weaker thing, and that's how the heart muscle works. So that's important to know for this a little bit, just to understand kind of how the cells are put together in the muscle. And then it's not important for this, for 4 leads, but this is a good spot to mention it, if anything. But all this stuff like myosin, actin, that make up the parts of the cell that kind of stretch and the structure of it, there's also a an enzyme in there called troponin, and troponin is only released when there's injury to the muscle. So sometimes you'll have someone who doesn't present normally for a heart attack, but on the monitor they're showing heart attack signs, and the thing they'll do in the hospital is they'll check troponin levels, because that could indicate a different mechanism behind a heart attack. So elevated troponin is also kind of like a heart attack in a way. So, or when you do have a heart attack, you'll have elevated troponin as well. So that's something that you can check in someone that doesn't present normally in a heart attack. And that's not important to know for this, like I said, but it's worth mentioning. So we're going to talk about pacemakers and inherent rates. So pacemakers, those are not the same, although there are pacemaker cells and pacemakers. This term pacemaker refers to something different. So a pacemaker, or the pacemaker, is whatever part of the heart the initial impulse is being generated in. So our heart, it has a certain order that it'll go in, because we don't want to just like have one thing fail and just like, oh, okay, you're done, and die. So our heart has backups. So as we discussed earlier up here, the SA node, that's what normally initiates an impulse that then conducts through the heart. If the SA node fails, we don't want to just die. So we have the next best thing take over, which would be the atria. It doesn't have to be a specific area, it could be anywhere. Like it could be over here, it could be over here, it could be in here, it could be there. So anywhere in the atria, doesn't matter where, one of those cells can randomly create an impulse, which will then travel through the heart and conduct a beat. So in that case, the atria, or that one spot, the specific area of the atria, would be the pacemaker, because it's creating the heartbeat in that case. If the atria fail to initiate a beat, then the AV node will take over as the pacemaker. And then if that fails, somewhere like along in here, which is the junction, as it's called, the junction will take over as a pacemaker. If the junction fails, somewhere, doesn't matter where, just some random place in here, in the ventricles, any random cell will take over as the pacemaker. So for each of these areas, there's something called an inherent rate, which is the rate that they'll normally generate impulses when they're functioning as a pacemaker. So the SA node is 60 to 100 beats per minute. And that makes sense because a normal heart rate for an adult is 60 to 100. And that's because the SA node is normally our pacemaker. If that fails, I'm just going to abbreviate this because I'm not going to write the whole thing out. The atria take over, and they have an inherent rate of 40 to 60 beats per minute. If the atria fail, then the junction will take over, the AV junction. And the junction has an inherent rate of 20 to 40 beats per minute. If that fails, the ventricles take over with an inherent rate of 20 or less. To less. So that's kind of how that works. So inherent rates, again, are whatever a pacemaker will fire at when it's functioning as a pacemaker. And then the pacemakers are the area that's generating the impulse that creates a heartbeat. So the SA node starts first. If it fails anywhere in the atria, any random cell will take over. If that fails, the AV junction will take over. If that fails, any random cell in the ventricles will take over. And the interesting thing is that Heart cells have something called automaticity, which means they have the ability to generate their own electrical impulse without any external stimulation. So if you take a heart cell out and put it in a petri dish, it will still be depolarizing or contracting because it can generate its own impulses if it needs to. So the other cool thing is if you put two in a petri dish and they'll be doing this, just beating on their own, but if you bring them close together, they'll start going in sync. And that's how the heart usually works. But they have that ability just in case something fails. Any random cell can generate an impulse to take over. So now we're going to talk about ectopy and escape. So ectopy is, or irritability and escape. Ectopy includes irritability and escape. So it's any random beat that's not sustained. So if you have a normal heartbeat and then randomly you have like what people refer to as a skipped beat or just a random beat in there that's not consistent with the rest of them and comes from a place other than the pacemaker at the time, that's called an ectopic beat. So ectopic beats or ectopy can be caused by irritability or escape. So irritability is the first one, and with that it's just like back in like elementary school or something, you had that one kid that like knew the answer to everything, or at least he thought he did, and like he just could not shut up and like he had to say it, and the teacher's trying to call someone else and he's sitting there like this, like raising his hand, and teacher's trying to ignore him like nope, and they're kind of asking everyone else like anyone else, and then eventually he just it's boring, like yells the answer out. That's kind of what happens here. So a cell just gets irritable and eventually just blurts out and generates an impulse for just a single beat. So that's an ectopic beat. So irritability will come quicker in the cardiac cycle. So as an example, I'm just going to draw it simply since we don't know the waves of heart rhythms yet. I'm just going to do this. So we have a beat there, 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 there. Then we have one like there. It would be this one right here. That would be your ectopic beat caused by irritability. Because even though I didn't do a very good job at drawing, I tried to make these equally spaced so everything looked somewhat the same and spaced out. And then we just have this random one that came too soon. That would be an ectopic beat caused by irritability. On the other side of that, we have escape. So escape is basically your heart is like it's basically it likes to jam out, so it really likes cool beats. Haha, get it? Beats, heart. Haha. But it kind of anticipates the rate that your heart's firing at, so all the cells know if your heart is beating like that, it knows to expect that. So all your cells are sitting there just kind of jamming out. But then what they do is if that heart misses a beat, their job is to take over for that impulse to get the heart back to where it should be. So that's an ectopic beat because it's a random one, but it'll come later because it only happens when the heart's expecting a beat or the cells are expecting a beat and there isn't one. So for an example, do this along with me. What I'm going to do is I'm going to clap my hands to represent a heartbeat. And your job is to clap whenever I miss a clap. So I'll do it at a certain tempo, get used to the tempo, and if I miss a beat, it's your job to take over for me. So if this is our heart rate, you would take over any time that I fail to clap at the expected speed. So the reason for that is either it takes like a reaction or it's a reaction time because you have to wait for me to miss one. See? So if you're waiting and then you like did that, it was probably late because you had to recognize that I missed it and then quickly react. So the heart cells are the same way, and that's why an escape beat will be later than expected. So I'm going to do this, draw this out again. We've got one there, one there, one there, So this one would be, whoops, sorry, just kidding. So this one would be the escape beat, or the ectopic beat caused by escape, because we had that at a normal time, but then right about here, that's where there should have been another beat, and there wasn't. So then your cells had to recognize that within this time, and then actually initiate a beat themselves right there. So that's irritability and escape. Again, to recap, it's just a single beat. Occasionally it can be like a 3 beats or more beats, but it's a non-sustained beat that it comes from a place other than the pacemaker. It's called ectopy or an ectopic beat. The two causes are irritability and escape. Irritability happens early in the cardiac cycle. Escape happens later. So now we're going to talk about leads and vectors. So how I was saying at the beginning of this video, there isn't really a 4 lead. There's just 4 electrodes or wires. But there's 3 leads, technically, is the correct way to say it. And the way that works is the electrodes themselves aren't leads, like I said. They create the leads. So a lead is actually the spot between 2 electrodes. So that creates this little thing right here called Einthoven's triangle. So it assumes someone's standing with their arms out and their legs together, which they don't actually have to be in that position for it to do it correctly. I don't know how, but what it's doing, so I'm going to draw the heart. So these leads, they look at each other, and they just monitor any electrical activity that happens between them. So the right arm lead, this is going to be considered a negative electrode. This one right here is going to actually be a combination, but it's positive for this side, and then going down there it's negative. Then down here is positive. And then again, we do have one over here, but that's just a ground, so it doesn't count. It doesn't do anything. So the right arm looking over to the left arm makes up lead 1 right here. So lead 1 is going to look from there to there and measure any electrical activity that happens. So when the heart beats, it starts up in the SA node, goes through here, down, up, and through the Purkinje fibers. So that movement of electricity is monitored by these, and we're going to get into how that translates to an actual waveform, but that's all it does, is it monitors that. Then we have this one looking down to your left leg, this way to that way. So first of all, I'll draw it over here. Heart. So lead 1 kind of looks that way. Then we have that, which is lead 3, and then we have kind of that view, which is lead 4, or I'm sorry, lead, okay, let's try this again. So this is lead 1, lead 3, and this is actually lead 2. So I didn't need to draw that, whatever. So from there down to here, back and forth, 2, lead 2, here and across, lead 1, here and down is lead 3. So that's where we get our leads from. It's the space between 2 electrodes. And I think we talk about it next, actually. I don't have my notes. So that what's measuring is direction of electricity. So that's called a vector, which is the direction. So for instance, if a plane is traveling from, say, one side of wherever to another side on another side of the country, chances are it's not going to go directly that way. You know, it might have to go around, above, or below clouds or bad weather. So it won't be going that straight direction. Like if it's going from east to west, it's not going to stay going west. You might have to turn to the north and go up or down. And so what a vector is it's the overall direction. So overall, the plane is still going west. That's its route that it's going. It's just not always going exactly west. But the overall vector, as it would be called, is a westward vector. So in our heart, because it spreads to all the individual cells, it kind of goes all different directions, even though it's still flowing in one primary direction. And if you recall, it kind of wraps around the atria and then it comes down the bundle branches and up the sides, so it changes directions. But overall, the electrical impulse is going from the SA node to the ventricles, so it's going in one direction. Another way to illustrate this is this map. So say a person works over here, but they live, well, let's say here. So to get to work, they might have to come down this way, over there, up to there. They might actually even come down this way, go this way. Say there's some weird detour, they have to go that way, and then they get to work. So see, they went all these different directions, but overall, this would be the direction of their vector. It would be, we'll say this is east and west, so they'd have a westward vector. So this line, this arrow, is their overall, is the vector, which is the overall direction they're going in. And that helps to not get confused by looking at all these little small changes they had. And that's how our heart works, because it would, an EKG would mean nothing with, if we measured all the directions it went in, because it's flowing all different directions as it spreads, so that would be useless to us. So instead, EKGs interpret it and show us the vector, so the overall direction it's flowing in. And vectors are going to have to do with what we talk about in this section. So we're going to talk about positive and negative deflections on a tracing, an EKG or ECG tracing. We're going to talk about the paper itself and what it means, the different graph things like you see in the background here. We're going to talk about waves and intervals. So there's two types of leads or electrodes. There's bipolar and unipolar. So 4 leads or 3 leads, the limb leads, those are bipolar, and that's because we have an electrode here, we have an electrode here, and it's monitoring the direction of electrical flow between them, so in this space right here. So that's a bipolar lead. A unipolar lead is just one electrode that looks in one direction. So it will just look that way and just monitor any electricity in that one specific spot that it's looking directly down on. Whereas these will monitor anything within the area between them. So with a bipolar lead, there's going to be a negative and a positive like I showed you on the Einthoven's triangle. So if we have a negative over here and a positive there, if the electrical vector or direction goes away from a negative towards a positive, that will cause a positive deflection on the EKG, on the actual tracing. If an electrical impulse goes away from a positive towards a negative electrode, that will cause a negative deflection, like so. If it goes at like a 90-degree angle, it will either not do anything, or usually it'll make a little biphasic, as we call, deflection, so up and down kind of. And especially in, I guess if it's like at an angle more like this, that's when you'll see it. It'll be a smaller complex, which complex means like the whole. We'll talk about that later, but the whole size of the deflection will be smaller. Instead of like a big one like that, you might see kind of just a small little one. and that's because it's not like coming straight at it, it's kind of at an angle, but still coming kind of towards it. And then yeah, if it's completely sideways, you might not see it at all. It might just be a flat line like that. Unipolar leads are positive, and so they actually, even though I drew the arrow that way, they're measuring just any electricity that comes at them. So if it does come at them, it goes up. If it goes away, it goes down. Now, if an impulse travels past a unipolar lead, I'm going to draw it, let's see down here. So along with this line right here. So as it starts, it's coming closer, closer, closer. Then if you see it's lined up, and then as it passes it, it'll go away. So that being our baseline, so it comes close, passes it, goes farther away, so it creates biphasic deflection. So EKG paper is going to be what we talk about now. EKG paper, it's going to have these big boxes that contain 5 small boxes within it. And then at the top of the paper we have these little hash marks, and these are going to be what tell you seconds. So let's see, it would be like 10.1. So yeah, so like from each one of these, it would be like 0.1 second. So go 1, 2, 3. That would be 0.3 seconds, or 3 seconds rather. So it's a second each. So if we looked at 6 of these, that would be equal to 6 seconds. So you could count how many beats you have in there and multiply it by 10 to get your heart rate. Another way to do it, since we're talking about it, might as well mention how to count heart rates on these, is you want to look for the biggest spike and see if it lines up with the dark line here. From there you count how many dark lines, and in order, it starts out at 300, then it goes to 150, I believe. 300, 150, yeah, and then 100, 75, 60, 50, 40, so on, like that. So you can count that, but I think we talked about that a little bit later in here. I just wanted to quickly show you that. But back to the paper here, each small box, so just this tiny little one here, each small box equals 0.04 seconds. There's 5 in each large box, so that means these large boxes equal 0.20 seconds. Let the dog out. So 0.20 seconds, and then up and down is just voltage basically. So we refer to it as millivolts, or sometimes we'll also it'll just be like a measurement, like a distance wise. So we'll use millimeters, because like in 12 leads with heart attacks, we want to see a certain point of the EKG and see if it's elevated above where it should be. So if this were our baseline and it's up here, the space between here and there, it's 3 small boxes above, so we would say that they have 3 millimeters of elevation. So, but that's not important really in this course. That'll be in the next one. But that's how the paper is. again, if you hit print on the monitor, it'll print out a 4-lead until you hit it again to stop it. A 12-lead, it'll print out a specific amount, and each lead that it shows will be a 3-second time frame. But the big thing to remember with this is just that the small boxes are equal to 0.04 seconds, and the large boxes are equal to 0.20 seconds. And there are 5 small boxes per big box. So now we're going to talk about the waves of a normal heart rhythm. So we have oh my gosh. Like that. And that was a terrible drawing. But so this is equal to 1 heartbeat. And let's see if I can try it one more time and see if I can do it better. Okay, that was actually pretty good. So we're going to erase the other one. So the waves go P, QRS, T. So I'll write that over here. P, Q, R, S, T. And QRS is kind of together, and we call that the QRS complex. Oh god, I don't want to write that, but I'll do it anyway. Complex. And I'll talk about that here very soon. So the P wave is this first one between here and here. P wave. So like, I'll do it in a different color, but like right here, right there, there, and there, and this like kind of a straight line across like that. This is our baseline, which is where things are at when there's no electrical activity. So it's also referred to as the isoelectric line. So when the wave first comes above baseline and goes upwards like that, that's where the P wave starts. When it comes back to baseline, that's where it stops. Then the first deflection down from baseline is our Q wave. So Q wave. Then once it goes from down there all the way up to this top part, that's the R wave. Then from there down to here would be the S wave. And altogether, we call that the QRS complex, and it represents ventricular depolarization or contraction. So we'll talk about the rules of the waves in a second, but that's what those are. Then from here, where it goes again above baseline to where it comes back down, that is your T wave. So the P wave represents atrial depolarization. So that's when the impulse is traveling through your atria. So like the SA node and the internodal pathways, that generates a P wave. Then it comes back down, this flat line right here, between the P wave and the QRS complex, that's actually not a complete no electrical activity. It's just so slow that the machine thinks it is. And that's when the impulse is trying to get through the AV node, because those fibers, it slows it down like I said. It goes fast and slow. That slowness, that's what generates that little area between the P wave and QRS. So that's when it goes to the AV node. Then the QRS altogether is ventricular depolarization. And then when it comes back up and we have this positive deflection above the baseline, that represents ventricular repolarization. So that's like when the ventricles are basically recharging so they can beat again. So ventricular repolarization. Atrial repolarization occurs at the same time as the QRS complex, and the QRS is way bigger, so it kind of drowns out the atrial repolarization, so we don't see it on there. So the rules for each of these waves: a P wave, like that, has to be normal. Rather, it has to be symmetrical. It has to be upright and round. And it has to be upright and lead 2. So if I didn't really, yeah, maybe that'll come up later, but if not, over here, if that's the heart, if we draw Einthoven's triangle again, like that, this is lead 1, this is lead 3, this is lead 2. So the heart is slightly tilted in the chest to the left. So if you think about the direction that the impulse travels through the heart, it starts up here, right? And its vector, or its direction, is kind of that way, right? So lead 2 looks from up here to down there. So that makes it a really good lead for looking at heart rhythms in, because it follows almost perfectly with the vector of the impulse. So lead 2 is, lead 1, 2, or 3 work, but lead 2 generally is a good one to look at. And the upright part, we want the P wave to be upright and round in lead 2. Well, round in all leads, but upright in lead 2. So those are the rules for it to be a P wave, or a normal P wave. Upright, round, upright in lead 2, round, and symmetrical. So if we have, for instance, a P wave that looks like this, or one that looks like this, or one that looks like this, those are all abnormal. And that means that it came from somewhere, the impulse came from somewhere besides the SA node. So that round, symmetrical, upright appearance is what tells us it's coming from the SA node, or the sinoatrial node. When you have like the weird, like jagged ones like that, or anything like that, weird shapes to them, that's an indication that it's coming from the atria. And then we'll talk about this when we get to it later, but if it's negative, that means it's not coming from the atria or the sinus node, it's coming from somewhere below. I'm going to erase all this so I can go on to the next one, or most of this, rather. So then, in our QRS complex, for a Q wave to be a Q wave, it has to go directly down from baseline, like that. So if it even goes up just a slight bit like that and then down, that's not a Q wave. It has to be completely at baseline and go immediately down to be a Q wave. Those are the rules. Then for it to be an R wave, it has to go above baseline. So that can be either after the Q wave, so we got a Q, then the R, because it goes right here, it goes above baseline, that makes it an R wave, and it stops up here. Technically it goes down, but that's what it has to do to be an R wave. If it goes, it's pretty much always an R wave as long as it goes up. So like if it goes like this, without going down first or after, that's still an R wave. It just has to go above baseline. Then for an S wave to be an S wave, it needs to go below baseline from above. So if we have just an R wave, and then we have that, that would only be an R wave because it did not go below baseline after being above. So that's your baseline. However, if it does this, whoops, that would be an R or an S wave rather, because this is your baseline, right? So it went above, making it an R wave, and then it came down, but it actually passed baseline, which makes it an S wave. So it's possible to have some waves and not have others, and that can be totally normal in some cases. So we always still refer to it as a QRS complex, even though there might not always be one of those waves. So for instance, this is in fact a QRS because we have the Q drop down from baseline, we have an R because it goes back above baseline, and we have an S because when it comes down, it again passes baseline. Now if we have this, it goes below baseline, making it a Q wave, but it doesn't go above again, so there is no R wave, and it has to come from above down past baseline to be an S wave, so this would just be a Q wave. This would just be an R wave because it goes above baseline, but then when it comes down, it does not go past baseline. And then, let's see, that's pretty much, oh, we can have this, which would be a QR complex because you have it drop down from baseline, it goes above baseline, making it an R wave, but it doesn't go down past it. But no matter what combination it is, we still just refer to it as a QRS complex. And then for the T wave should be asymmetrical, so it should kind of do this. So if you draw a line from the center, it should be asymmetrical on these sides. And that again just represents repolarization. Inverted T waves like this are bad, or they can be bad. Flattened ones or slanting wrong way, or like that weird concave shape, that can be bad, but that's not for this video, that'll be a different one. So hopefully that makes sense on all the waves. Just watch this part over and over again until you understand, if you didn't understand any of that. Now we're going to talk about intervals. We're almost done. So intervals, I know I'm kind of going through this part fast, but like I said, just rewatch and eventually it'll click, hopefully. So intervals. We have So we have an RR interval, which is the first one. And that is, again, the R wave being, or the peak of the R wave being up here. The RR interval is the distance from here to here. And that helps us determine if the heart's beating at a regular interval or irregular. So whether the overall beats are regular or irregular. And we also use that to calculate heart rate. So that's what RR interval is. And again, so if this R wave is right here, we'd want to look for one that's right on a dark line. We count how many dark lines there are until we have the next R wave, and that gives us a heart rate. So if we had one that was here and here, it would be 300, 150, 100, 75. So this person's heart rate would be 75. So now we're going to talk about PR interval. So the PR interval is from the start of the P wave, right here, to the start of the R wave. So right here technically, but we usually do it to like there-ish. Because usually the Q wave shouldn't be wider than one small box, so you pretty much just measure from there, or from the beginning of the first deflection up or down till the first next deflection, which should be the beginning of the P wave to the beginning of the QRS. So from there to there is called the PR interval, or PRI. And the PR interval, that tells us if there's any blocks, like in the AB node, with it going through the node. So we measure how long it takes, and it should be less than or below 0.20 seconds, which, if you recall, is 5 small boxes. So 5 small boxes, or should be less than 1 large box. That's our PR interval. So then over here we have from there to there, and we've got about 4, 5, 6. So that one, there's 6 small boxes, it looks like, between the start of the P wave and the start of the QRS. So that would be considered a long PR interval because it's greater than 0.20 seconds, or 5 small boxes, or 1 large box. Then we have our QRS complex, which we measure from the beginning of the complex, whether it be a Q wave or just an R wave or whatever. So we measure it from here. Then after the QRS complex, there will be a point where it comes back to baseline, and once it does, you'll see it go from a vertical position to start to slant to the side, and the line will usually be a little bit thicker right there, and that is called our J point. And the J point is where we measure to. So you measure from the start of the QRS to the J point, and it should be less than 0. Should be less than 0.12 seconds. So that would be less than 3 small boxes, or yeah, that's really the only way to do that. So it has to be 3 of these small boxes or less to be normal. Otherwise, it's called a wide QRS, and that equals 0.12 seconds. And we measure from the beginning of the QRS to the J point. Then we have, really the only other one we have is a QT interval, which is some measure it from the start of the Q wave, which I guess is right, or some, I think, measure it from the R wave, I don't know, but basically from the start of the QRS to somewhere after the T wave. It's actually really tricky to tell, and your monitor will tell for you. On the paper of a 12 lead, it'll say what the QT is at and what it should be at, because it varies from person to person on things that are way beyond me and way beyond basically anyone except a computer. But one way that you can do this, although I really wouldn't, just because it's kind of controversial, like as far as whether it's accurate or the right way to do it, so I wouldn't even worry too much, but just for your own personal evaluation, I guess, when you look at an EKG, you want the space from, or the amount of distance between start of the QRS to the end of the T wave to be less than half the distance of the RR interval. So here we look how far it is from there to here, and we see if from here to here is less than half of that, so less than this halfway point. If it isn't, that's a long QT. If it is shorter, then that's normal. So we think. That's again not super accurate, and you know, I don't think anyone will listen to you unless you're telling them directly off of the paper what it says, and that's one time when you do want to listen to what the machine says. So that's pretty much it for intervals. Now we're going to go over the steps of interpretation, and then we're going to interpret some rhythms. Obviously, we don't know the specific rhythms yet, the names, but what we're going to do is we're just going to determine intervals, calculate heart rates, and kind of check all the different waves to see if they meet those criteria that I mentioned in previous slides. So the steps, there's not really a specific way, like even in the textbooks, it doesn't always tell you a specific way to check these things, but this is the way that it was taught to me, and this is the way I do it. So you can do it this way, or you can do it another way, just as long as you check all these things. So first, look for regularity. So you check your RR interval to see if they're at a somewhat consistent distance. If not, it's irregular, possibly. Then we calculate a rate. Then we assess for P waves. Then we check intervals. And then based on all that information, that's all we need to be able to name the rhythm correctly. So we'll name whatever rhythm it is. So let's practice. So with this one, when we come up to it at first, we're going to look R wave to R wave, and we're going to see if those look about equal distance. So we've got 3 whole ones in there, and then so we got about 5 large boxes. Then we have 1, 2, 3, 5 large boxes, and 5 large. So you'll get quicker at that with time, being able to determine how much is between them. But these are all 5 boxes between each R wave, so it's regular RR interval, therefore the rhythm is regular. I'm going to put that up here. Rhythm is regular. Now to calculate a rate, we're going to look, we would want to look for an R wave like this one that's like right on a dark line. Preferably you count forward to the next one, but I guess in this case you actually could, because they're all consistent, I guess you could count back, but I don't know. Like usually it also says on the paper, and that's another thing you can trust, is what it says on the paper is a heart rate. So usually we just use that, but I've been known to do it this way backwards. I don't know if that's okay or not, but it's always been the same as what the machine says, so must be. But we'd count 300, 150, 100, 75, and a little bit more. So they're going to be somewhere below 75 in the like 74, 73-ish range to 75. So we're going to put that here. Rate is 75, and with that we're looking for it to be at the normal rate of between 60 to 100. So 75 is a normal rate, so we're all good there. We're regular, regular, normal rate. Now we're going to evaluate P waves. So we want to make sure there's 1 P wave for every QRS complex. We want to make sure there's no missing P waves or no extra P waves. So we do have one right there. Got one right there. Got one right there. And we've got one right there. So these ones actually look a little bit different. They are all upright, and we can just assume this is lead 2 because that's the most often used for this. But they are upright in lead 2. They don't really all look the same, but you know, close enough. We'll just call it close just for the sake of simplicity. So we have no extra ones, no missing ones. There is one before every QRS complex. They're all upright and round in lead 2 and symmetrical, even though they're not. But so we're just trying to make this simple, so we're saying everything's normal. So P waves, check. Now we're going to check our intervals. So we're going to start with QRS, starting there and coming to right there, because our J point is right here. So that's going to be, yeah, so that's like 2 small boxes, so it's QRS is 0.08 seconds, or 2 small boxes. So that is normal. Our PR interval, which is from right here to right there, is less than 1 large box, or 5 small boxes. So PR interval, check. So based on all that now, we can use that information to determine this is a normal rhythm, or in this case we would call it a normal sinus rhythm, because we can tell based on the P waves it's coming from the sinus node, making it a sinus rhythm as it's called. It's not too fast or too slow because the rate's normal, and all the intervals are correct, so there's no AV node blocks. With this one, we have, it's hard to tell if it's normal or not, like regular or irregular, because we have this right here and this right here. What do you think those are? Those are ectopic beats, right? Because you can tell they're not from the same place as the pacemaker, because look how weird those are. Their shape and size, it's different than these right here. So that's an ectopic beat. So after an ectopic beat, there's usually a little pause before it resumes. So we can't use this one. We can't use this one directly after to determine regularity. We have to go to the next one, which this one, excuse me, which this one actually looks a little bit early. So it's hard to tell if it's just an irregular rhythm or whether this too is an ectopic beat. Gosh. So in this case, what I would do is I would print out a 3-lead, hit the print button, and let it print out for a while. Then hit it again so you get a nice long tracing. So that way you can find a spot where there are no ectopic beats and determine if it's actually a regular rhythm and there's just these 3 ectopic beats, or whether it's irregular and this right here is actually a normal one. That's what I would do. But we know we have 2 ectopic beats, and they do come early, it looks like, instead of being way down by these ones. So that would mean it's an irritability thing. So it would be also known as a premature complex, as we call it. And we'll get to that in later lessons. But so no way with this long of a tracing to determine if it's regular or not. But we know we have 2 ectopic beats caused by irritability. And possibly another type of 1 too, but yeah. So then down here, our R interval is regular. Oh, sorry, I didn't even get into that up here, but it's RR is irregular, but we don't really know that for sure. Rate, we don't count ectopic beats in our rate, but if it's irregular, we just count how many beats are in 6 seconds and multiply that by 10. So we got 1, 2, 3, 4, maybe 5 or 6, but you can't really tell because you need to see the whole thing. So in this case, it would be like 50, maybe 55, 60. So that's slow. It is coming from the sinus node, because if we look at our P waves, they're upright, round, in unison in lead 2. Our intervals are good. We don't count the ectopic interval. So PR interval is good, QRS is good. So this would be what we would call either sinus bradycardia or sinus arrhythmia, because it's irregular maybe, but just because of the rate, that actually tells me that this one in here was actually another ectopic beat from the atria. And you'll know all this by the time we're done with this course. But down here, these look pretty regular as well. So regular. The rate is, let's see, another way I do this is I just see what square it's on. So this one's like on the second one. I just count to the equals square. So second one here, 300, second one here, 150, second one here, 100, and then that one there's like 75-ish. So this is going to be a heart rate that's somewhere in the 80s, 90s-ish. So still normal, just on the quicker end of normal. We do have P waves, these guys right here. Divide it up, so this is the P wave. We do have one before every QRS. They're all upright and round, symmetrical. And we have no extra or missing ones. So P waves are normal. That tells us that this is coming from the sinus node. So, and that is consistent with the rate that we're getting. PR interval is about, it's actually a little bit long because it starts right here and then it comes out to here, which is about maybe one box past the large box range, so just slightly long. So there is some sort of blockage in the atrioventricular node. Our QRS is normal. It's less than 3 small boxes, or 0.012 seconds. So now that we have our intervals, our P waves, our regularity, and our rate, we would determine the rhythm and name it. In this case, I would call this one sinus tachycardia, and then probably, which we'll learn about later as well, first degree AV block. So sinus tachycardia with a first degree atrioventricular block. And I don't expect you obviously to know the rhythms now. I'm just showing you what the interpretation is and what you'll be able to do eventually, but right now we're just focused on getting those numbers, those specific things, in order to determine what rhythm it is. So this one is very irregular. The distance between here and then like there is big. There, that right there actually is an ectopic beat, I think. And the reason for that is because there actually is a P wave, which with the way everything else is here, I wouldn't expect that. And you'll learn that when we talk about atrial rhythms, but it's irregular. Besides that ectopic beat, we have no discernible P waves, and our QRS is within normal range. Our rate is, let's see, so it's like 80, 90, so it still looks like it's normal rate. It's just irregular with no P waves, but intervals are good. So in this case, we would name the rhythm, and I would call this atrial fibrillation with a premature atrial complex, or ectopic, from irritability. Then down here, same thing. And are these the same? These might actually be the same, just from different views. And that does actually look like an ectopic beat to me. Either this one, probably that one, or this one maybe, but or it could be a couplet, as it's called, of what's the word? Ectopy. But yeah, so this would be AFib, or atrial fibrillation, with premature atrial complexes. Now this one, we have an irregular rhythm just because of this gap in here, but we do have P waves before every QRS with no extra or missing ones. Our rate for this, assuming it was a 6-second strip, would be 1, 2, 3, 4, 5, be about 70. Even though there's this gap in here, and there's usually a gap after an ectopic beat, this one is not an ectopic beat. I can tell because the P waves match the other ones, and so does the overall QRS complex. It's all identical to the other ones. so therefore I can tell that it's coming from the same place and not an ectopic beat. So it is, otherwise it's kind of, it is irregular though. So irregular, it's about 80 to 90 beats per minute. We have P waves with no missing or extra ones. QRS is wide because we're measuring it from here to the J point, which, like I said, how it gets thicker as it goes to the side, it would make the J point right there. So this distance is much larger than 3 small boxes. So that's wide. That's terrible. QRS is wide. Then our intervals, PR interval from here, from here to here is normal. So it's just the QRS that's off. So with all that information, we name it. I would call this a sinus arrhythmia with sinus pause or sinus arrest, and a wide QRS. So this one, our interval, we have this big gap right here, making the beat irregular. Calculate a rate. This would be a rate of about 40, because when it's irregular, we just count how many QRS complexes there are within 6 seconds and multiply by 10, because we can't do the dark line method when it's irregular because it's not reliable. So heart rate's 40, it's irregular. And then, let's see here, if I measure this out. And then we have, if we go to P waves, we do have them. They're all identical, but we have this extra one here, but we don't have any missing ones. Our QRS starts here and ends about here. So that's about within normal range of 0.0 or 0.12 seconds. So with all that, knowing it's irregular, it is at a rate of 40, and P waves are good and intervals are good. I would call this a sinus bradycardia most likely. It's possible it could be a 3rd degree atrioventricular block, but I don't think so because there's usually not much irregularity, if any, in those types of rhythms. However, we have this extra P wave, which tells me that there was a sinus pause or arrest. So this P wave didn't generate a QRS. It's on its own, and that could be the cause of this big gap in irregularity, because from here to here and here to here actually look about normal. So chances are this actually is a regular rhythm that's just interrupted by a sinus arrest or a P wave that doesn't generate a QRS. Our PR interval, however, is very long, but it looks consistent with each one that does generate a QRS. So there, 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 and there, that looks normal. So this is a type of AB block that we would call a 2nd degree type 2 atrioventricular block. So my diagnosis of this patient, let's real quick just so that actually is correct. The rate looks about that. So I'd call this a sinus bradycardia with a 2nd degree type 2 atrioventricular block. This one is irregular, no P waves. QRS is normal, and rate is 1, 2, 3, 4, 5, 6, and rate is 90, maybe 100. So I would call this rhythm atrial fibrillation, AFib. This, no P waves, it is regular. We can determine PRI. QRS looks wide. So this is what we would call ventricular tachycardia, or VTach. Then this one, if you'll notice, it doesn't really go down before, or it doesn't go up before down, so this is a Q wave. Not everyone has Q waves, a lot of people don't. So it's Q wave, just fun fact. We do have an ectopic beat right there, and right there, and right there. So this is what we would call a trigeminy of premature ventricular complexes, or PVCs. Otherwise, we have, it's kind of hard to determine if there's P waves. I think I see some, but it's not very clear. So let's see here, and it's hard to tell if it's regular or not just because of the ectopic beats. But in the places like from here to here and there to there, that looks fairly normal, but it's hard to tell. So this could either be AFib, and those aren't P waves I'm seeing, or this could possibly be something called a wandering atrial pacemaker with ectopic premature ventricular complexes. Don't worry about all that right now, but those are the steps, like what we're working on right now, the whole reason. This is very regular. There are no P waves. There probably are. It's just that when beats get faster, they kind of push the complexes and things together. So chances are that the P wave is actually hidden within this T wave right here. So these are both T and P. But we can't tell which is, or we can't discern P waves, so no P waves as far as we're concerned. The rate, starting on this guy right here, is a good one. Got 300, 150, so their heart rate is at 150. No discernible P waves, regular. QRS is normal. So in this case, because we can't really tell what's going on and it's fast, this would be what we refer to as SVT, or supraventricular tachycardia. If I could see P waves, that would count as something called sinus tachycardia, because I would know it came from the sinus node, but I can't tell that here. Now I'm real quickly going to go through some 12 leads. I'm just going to show how I interpret them and show what you'll be able to do once you watch this basic EKG interpretation, and then my 12 lead one, which is coming out later. This is just with experience, as it says in the title, with experience, what you can tell by a 12 lead or by an EKG in general. So this one, it's regular. I don't see any discernible P waves. QRS is wide. So yeah, this one is possibly something called an idioventricular rhythm, or a junctional rhythm. And then we move on into the 12 lead steps. So I'd call this a junctional rhythm at a rate of about, let's see here. There's not really any good ones. So at a rate of 100, so it could either be a junctional tachycardia, or it could be VTach, ventricular tachycardia, although I'm not so sure about that one because it's usually a little bit quicker, even though it's on the cusp of what you could consider a VTach rate. But this is likely junctional tachycardia. Electrical axis is between 0 and 90 degrees, or vector. We have inverted T waves, and the inferior leads V2, 3 AVF, or at least V3 or V2 AVF. No ST elevation or pathological Q waves. Other than the inverted T waves, no ischemic T wave changes on lead 3. And same with my septal, anterior, and lateral leads V5, V6, AVL, and lead 1. And I think that inverted T is actually just a result of the weird complex. They do have a left bundle branch block, which in order to rule in or out heart attack, you need to follow something called Scarboza criteria. And also that makes that along with the rhythm, I think this is, that makes the inverted T waves, like I said, not really diagnostic in any way, because it could just be from the wide complexes in the bundle branch block. But yeah, I'm going to call this junctional for now. Possibly a heart attack, but we need to follow Scarboza criteria due to left bundle branch block. And this person may possibly have hyperkalemia, so high potassium levels. And yeah. So this one right here, this person is having a heart attack. They have a regular heart rate, regular heart rhythm. Rate is about, so rate's like in the 60s, low 60s, high 50s. It is regular. Our PR interval is long, so it's going to be a first degree AV block, no extra or missing P waves. And our QRS looks good. That's good, yeah. So our QRS is good. So in my inferior leads, lead 2, 3, and AVF, I do have ST elevation is what it's called. The J point's up here, while the baseline is down here, which means that is ST elevation, because that is the ST segment from the S wave to the T wave. So we have ST elevation in 2, 3, and AVF, which are the bottom side of your heart. So they're having a heart attack down there. We have reciprocal changes in V2, V3, and V1 maybe. Otherwise, no other abnormalities that I can see at least. So I'd call this a inferior wall myocardial infarction, and it's likely to be blocking the right coronary artery. The end. So good job if you stuck through that. That was way longer than I thought it was going to be. I knew it was going to be long, but that was intense. So thank you, even if you had to watch that in a few goes. Thank you if you watched all that. This picture says it all, man. It's a lot. But fortunately, that was the worst of it all. That's the hardest concepts to understand of it all. So if you can understand that by watching it over again, or if you have it down already from watching that, then good job. If you're discouraged by this, don't worry, because like I said, this is the absolute hardest part of EKG interpretation. After this, all the videos are going to be so much more easy because the big hard concepts were explained here. So don't let that discourage you from watching my future videos. They won't be as long, and I promise you they won't be as hard. This is a tough concept for a lot of people when they're starting out. This is hard. It's not an easy thing. So just keep working on it and practicing what I showed you here, and you'll be just fine. And I hope to see you in the next video. Thanks again for watching, and have a good day or night or whatever it is where you're from. Thanks again, and see you later.